So, before I start my talk, just a couple of sentences about me. So I work at the bank now, but I used to be an academic. If you were at the keynote yesterday morning, you might have seen a picture where I had a face sticking out from somewhere. I had more hair. Contrary to what Simon said, I was not on the original Haskell committee. There were two of us from the same university when the Haskell committee was formed, me and Thomas Jonsson, and we flipped a coin on who was going to be on the committee, and he lost. So I was on the committee later on. So I made the first publicly available Haskell compiler. So I've been around with Haskell for a while.
Lennart, just clarify. Lennart can't explain this clearly. What would happen was that at Glasgow, we would work on the Glasgow Haskell compiler, and Simon Peyton-Jones and Will Partey would sit down. They'd work very hard for months and months and months, and they'd do a release of the Glasgow Haskell compiler. And then 2 days, Lennart would do his new release of his Haskell compiler, and it would be much faster than ours. And then the same cycle would iterate.
Well, I did manage to release the first release before Glasgow because I stole the name that they wanted. The compiler was called HBC, which are Haskell B. Curry's initials. Anyway, so my plan for today is to show you simple embedded domain-specific language, and then I'm going to show you two embeddings. So there's something called shallow embedding and deep embedding. We'll come back to that in a little, and then I'm going to show you how you can generate actual machine code for your EDSL. So it was already said that EDSLs are something that Haskell is very good at, and I'm not really sure when something is an EDSL or not. I mean, it's just a library. I guess it depends on what sort of the target audience for the library is. If it's sort of meant for some kind of domain expert who's going to use it to do things in their domain or not. So I'm going to leave that out, what an EDSL actually is. So I work at a bank. Banks are very secretive, and you have to get permission to say things. So to avoid getting permission to say anything about what I work on, I'm going to talk about what other people work on that don't work at our bank. About something that they've done at Berkeley Capital instead, because they published a paper about it. So I couldn't possibly be revealing any secrets about what we're doing. So they have a DSL. I don't actually know the name of their DSL. Is there any BarCap people here? No, okay. So it's a DSL for describing exotic trades to value a trade. And this slide pretty much captures the essence of that EDSL. So you have couple of specialized types like dates and assets. I'll come back to assets in a moment. You can do things, you can add and subtract numbers and so on. I'm calling these numbers E-doubles instead of double is the usual Haskell type for numbers. These E's you should think embedded, so these are the doubles in my little language. By the way, I'm going to assume you recognize Haskell syntax. How many people here recognize, understand the Haskell syntax? Well, so if you don't understand something, just ask me. But I'm not going to explain Haskell syntax unless it's something really obscure. So we have some operations for arithmetic, max and min, some logs and doubles and so on. We can compare these things. There's a conditional construct. We can do some things on lists. And so the thing here that really makes this different from just sort of arithmetic is this observed functions, which takes an asset and a date and gives you back a double. And so assets are things like some stock, for instance, and you can observe what the value of the stock was on a particular date. So given an asset, like Apple stock and a date, you can see what the value of it was on that date. So depending on what you're doing, these are not necessarily dates in the past. You could be doing some kind of modeling, and these could be dates in the future where you have some models trying to predict what's going to happen. So here is the example I'm going to use in my talk. It's called best of. It has a list of assets and 2 dates, and it's going to tell you how much the best performing asset has increased in that, between those 2 dates. So what you do is that you have your assets, you map this function that computes a number called the performance, so how much has it increased. We get that by observing the asset at the later date, dividing by the observation of the asset on the first date, subtract 1, this is sort of the relative increase of that. And then you have all these numbers and you compute the max. So this is a very simple function, but it's a realistic function. It's actually one of the examples from the papers from BarCap that I mentioned. Just to show you something else that I'm not going to talk about, here's something called that computes a cliquet. I think it's called, I don't really know what these things are. I just work at the bank. I don't really know. So first, a shallow embedding. So a shallow embedding means that all these functions that we have, we're going to implement them in Haskell, and they're going to do what I sort of said they do. So the plus function will add numbers and so on. And so this way we're going to contrast this with the deep embedding later. So the advantages of the shallow embedding is that it's pretty easy to write. It's reasonably efficient when you want to run things, but it's not as flexible as the deep embedding, and I'll get back to what the difference is when we get to the deep one. First, some words about what the date and asset types are. We have to pick something. I mean, we're going to implement this now, so I'm going to pick these specific implementations for dates. So dates are just unsigned numbers, 32-bit unsigned numbers I picked. Could represent the number of days since 1900 if you're Windows, or you could have something seconds since 1970 if you're Unix, or you could have nanoseconds since the opening of the Smithsonian Institute if you're VMS, but doesn't really matter, except you'd have more bits if you need the nanoseconds ones. Also VMS is dead. Assets, I'm going to pick something really simple, so an asset will just be a list of date double pairs. So at the particular date it had a particular value. This is definitely not how you would want to represent it if you were doing this for real. You would have something where you could quickly look up the value at a particular date. But I'm going to make this simple so I can fit it on my slides. So here is the implementation of the shallow embedding. So the type E double is just regular Haskell doubles, and the booleans are just regular Haskell booleans. And the list type I had are regular Haskell list. And plus and minus and so on, well, they're just a regular Haskell plus and minus. So there are really only 2 functions that were not the standard arithmetic functions, so it's observe and con. So con is the conditional, and that's just implement by if then else. Then we have the observe that takes an asset and a date, and what it needs to look up this observation. So you have a list here of date double pairs, and you need to look it up. So I'm using just the Haskell list lookup function, and I'm saying if it's not in there, I'll say it has value 0. That's really stupid, but it made that line short enough to fit on the slide. Yeah, that's it. That was pretty boring. I mean, that's all we need to implement. Now we have this, we can take one of these things like the best of function, give it a few assets, give it a couple of dates, and we'll get the number back. Because there was only really observe in there that was anything that we needed to implement, and that was just a lookup. So let's move on. So if you have a deep embedding of an EDSL, you don't write functions that actually do what you're supposed to do. All these plus and minus and observe and so on, they will build a representation, sort of some kind of syntax tree that describes what you're going to do. So the advantage is that it's very flexible. You can do a lot of things with this syntax tree, and it can be very efficient. It's much more work to implement it this way, and it can also be much less efficient. Well, I'll actually have some numbers at the slides at the end. What do I mean by more flexible? Well, if you have a function, so in this shallow embedding, the best of function was really just a function that took a list of assets and 2 dates. The only thing you can do with the function, you can give it the arguments and you'll get the number back. Now we have built this representation of it, so there are lots of things we can do. We can run it, of course, we have to write some kind of interpreter that runs it, or we can pretty print it in some sort of mathematical notation or something like that. We can analyze it, we can see like what assets are actually used inside this and so on. So there are lots of more things we can do once we have it in this form. And we can compile it to machine code, which is I will do at the end here. So how do we do the deep embedding in Haskell? Well, first we have to have some representation for the things in our DSL. So there were a bunch of things you could, this is just a Haskell data type that says, well, I'll have some types for, or constructors for adding, subtracting, blah, blah, blah. These are exactly the functions I had. They will all have a constructor. Then we need some kind of constants. I mean, there are doubles, there are booleans, there are assets, there are dates that can also be in the code. So we need some constructors for those. So this is untyped. Well, there is the expert type does not carry any information about what type it is. So all of these are the same. So for instance, I mean, this expert has to be a double and that has to be a double. Otherwise the subtraction doesn't make sense. And in the conditional here, this needs to be a boolean and so on. But that's all gone here. There are ways to make this representation type safe, but I'm going to ignore that. I'm going to use this. I'm going to put another layer on top of this to make it type safe. So this type expert will never be exposed to the users. So sort of the people who are actually using the DSL. They won't see this. This is under the hood. So what they will see is a type called E, for embedded, if you will, which is, so E, the type E, it has a, it's parameterized over some type. So this is called a phantom type variable because it doesn't actually occur on the right. So this, the type here just sort of tags things to say, well, the expert you have is actually a double or a bool or whatever it is. But it's just an expert underneath, but it's been tagged with what type it has. So plus and minus and so on, it will now have types E double to E double to E double, and less than will be E double to E double to, no, bool. There's a typo here. There's always a typo. And so on. And if you want to have the types we had before, we can just make some abbreviations. So we want to use the standard Haskell syntax for things. So if we want to write plus, even when we're doing the plus for in our embedded language. So we can make a new instance. So we say E doubles are numbers too. And if you have something is in the num class in Haskell, which means you can use plus and minus and so on, there are these 6 methods that you have to implement: plus, minus, times, abs, from, integer, and signum. So if I write plus, it's going to be bin op add, and you can see what bin op is. Oh, yes. So it takes something that operates on expers, that is the add, It takes two E things and gives you an E thing back. So all it does is just sort of strip off the E thing from the first operand, strip off the E thing from the second operand, do something with the two expers and put the new E on it. And I've given it the most flexible type there is here. So these are not, again, not things that will be exposed to the end user. They will just see these things. They can write plus, minus, and so on. And that will construct the syntax tree underneath. Here are just some more to be able to use slash for division and to be able to write numeric literals in floating point format and exp and log. So this is sort of, if you have some embedded language that uses number, this is sort of the standard way of doing it in Haskell. The observe function, it just builds an observe node in your syntax tree. Less than builds a less node. Conditional builds a conditional node. They're all kind of boring. So something we'll want to do is to move between real values and E values. We need that because at some point we're going to interface our DSL code with real things. So I mean, we'll have two dates that we want to use in our best of function, and those will be real dates and not these embedded dates, not the E dates. So we will want to be able to lift values, say dates, into E dates, and we want to be able to go the other way around. If we have an E date, we want to be able to get the real date back out again. So lifting it, well, if it's a double, we just say tag it with double and so on. They're all just tagged here. So there's a new class here called values. So these are the acceptable values in our EDSL. So this exactly controls what things can go in and out of E. So there are only doubles, dates, booleans, and assets that can go in and out. And so the conversion the other way, that could possibly go wrong because it might not be a double here. I've just left out the cases where it goes wrong because, well, the way the rest of the code will be structured, it will never go wrong, or at least I claim it will never go wrong. So just to illustrate, so if we were to fire up GHCI, the interactive system, so we could write something like 1 plus 2, but we say the type is E double. So that means that the plus operator resolves to our special plus operator. Numeric literals will resolve using the from integer method. So we can just write 1 plus 2 and it will actually turn into this. So that is the syntax tree we built. But we use normal Haskell syntax. It's just a type that decides what the overloading will do. And here's some other example. If you use con 1 less than 2, blah, 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 we'll get this syntax tree. And of course, this is all typed. So if we try to do something wrong, like 1 plus 1 less than 2, we'll get the type error saying, couldn't match expected type double with actual type bool. And it babbles on a little bit because this is a double, this is a bool. So I think being able to make typed EDSL is great. I mean, I'm all for types. So if I make an EDSL, I want to make it typed as well. So the cool thing, if you want to make typed EDSL in Haskell, is that the type system is extremely flexible. You can really program the type system to make a type system that behaves like you want to in your EDSL. You don't have to sort of have arbitrary sort of infelicities. You can really program the type system. It can be quite complicated to program the type system, but it can be done. What can really suffer is error messages, because error messages are often in terms of your implementation rather than what the user wrote. So here, this error message turned out to be quite nice, but they're not always that nice. So there are advantages and disadvantages to having embedded DSLs. I learned a new word, neritic. It's apparently the part of the ocean that is between the shallow and the deep. So there was one type I didn't mention, the list type. So there's no doubt what it should be if we have the deep embedding. So the list type should be an E something. And I mean, using the Haskell list type to sort of be the tag for those lists, that seems reasonable. If we had shallow embedding, it would be this. So list A's would be real Haskell list. So this would build a representation, and this would be regular lists. But there's nothing that says that when we make an EDSL that we have to pick the same thing everywhere. Just because we're deep in some things don't mean that we have to be deep in everything. So in my particular example, I'm going to, in the best of function, I'm going to have the first argument, which was a list of assets, and then there were 2 dates. So I'm going to be shallow in the embedding of the list and deep in the embedding of the dates. So that's why it's sort of between the shallow and the deep. So exactly how you're going to do this, it depends on your domain. So I did it for simplicity for this particular example. So I'm going to mention what the differences are. So once you have an EDSL like this, there are sort of 2 times when the code runs in some sense. So you write something, 1 plus 2. That turns into this syntax tree. The syntax tree does nothing. We later on have to do something to the syntax tree, write an interpreter for it, or code generator, whatever. But first, sort of the Haskell code runs that does some processing. And then later our interpreter, or whatever it is, runs and does some further processing. So there are really 2 stages when things run. And I'll call them compile time and runtime, which is not really the compile time and runtime of the Haskell code, but of our EDSL. So this is the type I'm going to pick for my example, and this is the alternative. So here, the list of assets would be something that exists at runtime. Here, the list is a real Haskell list. It doesn't exist at runtime. It only exists when the Haskell code operates. So this is fine if your lists here are always of some fixed length that you know. You can sort of look at your code and you say, well, I'm always passing in 3-element list or whatever. Or you know it at the first stage of your processing, then this works fine. If you need to have a dynamic size of your asset list, then you need to pick this one, where you may be constructing the list of assets as the code is running. Then you have no choice, then you need this one. If it's fixed, you have a choice. You can use this one or that one. So I picked this one. I had picked the deep embedding, then I need more functions here. I didn't mention the things for lists, but I need some way to represent fold and map. Those were 2 more functions that were available. I need some way to have list values in there as well. And even here, I have made a choice that this thing, the function in the fold and the function in the map, they could also be expers, depending on if we're embedding functions deeply or shallowly. So I'm going to leave this out because I'm not going to use this. I'm going to use the shallow thing for the first argument. Okay, so now we need to take an exper and compute the value of it. There's a lot of stuff on this slide, but it's all pretty boring. If you've ever written an interpreter, it looks something like this. If we want to evaluate addition of 2 things, well, then we evaluate the 2 things. They better come out as double and double, and then we add the actual doubles and we tag it again to be a double, and so on. If it's a conditional, we evaluate the conditional. Depending on the Boolean, we will pick the first one or the second one, and so on. And observations, we use our lookup obs function. And all other cases, they were the constants E double, E bool, and so on. So this could clearly go wrong. I mean, if these are not two doubles here, there are lots of error cases. If this one is a bool and that one is a date or something like that. But again, I claim that I will never use it in a wrong way, because what's exposed to the user is not the expert. They can only use the E thing. They can only build things with plus and observe and so on. And they all construct things that are type correct. So the thing that you can actually use at the top level to compute things is this eval E function, which takes an E something into an A. And you can only do this if it's something that is a value that you can represent in your DSL. So the A here has to be double, bool, date, or asset. Those were the four things that I made instances of value. And you do it by, well, you pick off the E tag, do the expr evaluation, and you downcast it, or whatever you want to call it. All right? So this is an evaluator for the deeply embedded language. So now, well, in a little test here. A couple of dates, a couple of assets, and best of, it takes a list of assets, or rather it takes a list of E assets. So we need to take our assets and lift them into E assets. And it takes two E dates, so we need to take the two dates and lift them. And then we can evaluate that, and we'll get the double out. And if we run this particular thing, we get this to be 0.5, I guess. Don't ask me what it means. So now we're getting to the actual interesting bit. We're going to generate machine code for this, because this interpreter is kind of slow, which I will show you later on. So what is the LLVM? It stands for low-level virtual machine. So it's like assembly code, but not for a real machine. It's assembly code for a virtual machine. But the virtual machine is not like the Erlang virtual machine or the Java virtual machine or anything like that. It's a very low-level one. It really looks like assembly code for a real processor. It's just some kind of idealized processor. So it started out as a university project, and now it's mainly sponsored by Apple, which Apple are using this for a lot of stuff that actually runs on the Mac. So if you have a Mac, chances are that the LLVM is involved somewhere when you're running graphics, for instance. So the LLVM is a big C++ library, and what can you do with it? Well, you can somehow generate some LLVM code, and then you can do either a batch or a just-in-time compiler. So if you use the batch compiler, take the LLVM code, it will translate it into assembly code for, well, there are lots of processors like x86 and ARMs and Sparks and so on. Or if you use the just-in-time compiler, you give it some LLVM code, and it will generate machine code in memory for you, and you'll get a pointer to that function, and then you can just call that function. And you can use this from many languages. So it's a C++ library, but you can use it from C++, from C, from Haskell, from OCaml, and there should be a ... here, because there are other languages that have bindings to this as well. So I'm, of course, going to use the Haskell bindings. So yes, as I said, to use the just-in-time compiler, you build an instruction sequence, you call the JIT, you get the pointer to the code. It uses the C calling conventions, so you just call this code like you would call any other C code. unless you, I mean, you can have other calling conventions, but normally you do that. So there's also, the Glasgow Haskell compiler has a backend that uses the LLVM. That's completely unrelated to what I'm talking about, but it's there. It's another way to generate code. Instead of using the GHC's native code generators, you can generate LLVM code and from there go to whatever machine you're running on. So this slide has a lot of stuff. I only want you to look at the black stuff, not the gray stuff. So here's a function, 2 arguments, they are doubles, say x and y, and it's going to compute x plus x times y. So what you have to write in Haskell to generate machine code for this, or rather sort of the LLVM code for this, comes from these 3 lines. So if you've ever written assembly code, you can sort of see how this works. So, well, so the arguments will be called x and y. So you add x to x, we call that x2, and you multiply x2 by y, stick that in some temporary register, and then we return this temporary. So depending on what machine you're on, this will turn into a few machine instructions and add a multiply, some kind of return, and a few things in the beginning here to set up your activation record and so on. The rest of the stuff here is just to show you a complete example. So this is an example you could run. You could take this, stick it into a file and just compile it. If you've installed the LLVM libraries for Haskell, you can run this. This will take this function. After a few little things here to actually compile the function, you can call this function with the arguments 2 and 3, and it will print 2 plus 2, 4 times 3, 12. So that's what I'm going to use. So the basic idea now is to get an efficient EDSL is that instead of having an interpreter, we will translate our EDSL, because we have the syntax tree, we will translate it into some other language, and that other language is the thing that we're going to actually run. So when we actually run it, there is no Haskell involved whatsoever. We're going to run it in whatever this other language is. So if you were at the keynote yesterday morning, you saw John mention translating to C, which is another example of this. You have an EDSL. When you run that code, it doesn't run the code, it generates a C program, and then you have to compile the C program and run that. That's what you actually run. This is very similar. When you run the Haskell code, it will generate some LLVM code. Then you will run the jitter on that, so you get some machine code, and then you run that. So we do it all in the same process. They're not multiple stages, but it's sort of, when it actually runs, there's no Haskell involved. There's only the machine code generated by the LLVM. So as I said before, this is an example of a 2-level language, which is it's kind of like macros in many languages, or C++ templates. You have to think sort of on 2 levels. There are some things that happen early on when you have some of the information, and there are some other things that happen later on when you're actually running it and you have all the bits around. And you can use this to sort of control when things happen, how efficiently you do things. So for instance, if you know that you have a loop from 1 to 10, say, of something, you can then choose to either generate the loop and run it at runtime, or you can duplicate whatever you're going to do in the loop. You can duplicate that 10 times and have, so the actual looping happens at the first stage, and then the second stage will just run straight line code. So this is the same kind of decisions you have to make if you're writing a compiler. Are you going to do things in the compiler, or are you going to do it at runtime? But here you have control over it because you're writing your own compiler. All right. So I'm going to translate type correct expers that we have into LLVM machine code. And translation will proceed by type, so there will be a few different functions. Gen double takes an expr and will generate LLVM code that returns a double. So this gen type hides a lot of stuff that sort of involved in the actual type of the LLVM code generator and so on. So the LLVM bindings that I showed you a little example of before, that's another EDSL. It's the EDSL for generating LLVM code. And LLVM has a very complicated type system, but it's all programmed into the EDSL that you have available there. So it will do the kind of checks that are necessary for the LLVM code to be type correct. And that will, if you make an error in your LLVM code, so the LLVM code wouldn't make type sense, it will show up as a Haskell type error when you try to compile it. Anyway, so here is the function that generates the doubles. So we have to handle all the cases where a double can occur, or sort of what can generate the double. So, well, there are arithmetic, conditionals, the observe function, and you can have double constants. Oh, I forgot exp and log, but it doesn't matter. So I'm going to show you the arithmetic ones here in a moment, and also conditionals. Observations, the assets, I haven't told you really about how we're going to represent assets when we generate machine code here, so it's just a bunch of question marks, and I'll get back to that. Constants are easy. We just return the constant. There is some value of thing here that lifts things, real values, into LLVM values. So gen op double, it takes an opcode. This is an LLVM opcode, and it takes two things to generate code for, so let's look at that. So it takes an LLVM opcode, which happens to have this type. Yeah, maybe it can do an arbitrary thing here. But these two exprs have, the E1, E2, they have to be double things. So I recursively call E double to generate the code for the generating the first argument, generate code for the second argument, and then this op, you just, your opcode applied to two argument. If we want to go back here, no. This was the opcode: floating add, floating subtract, floating multiply, floating divide. So this is going to be one of those four. So this is where it actually happens. This is the thing that generates the LLVM instruction. Yeah, the type is scarier than the function. So you don't have to write the type. I mean, Haskell will infer it for you. I like to write them out. Conditionals, you don't really have to read everything here. Conditionals are a little bit complicated in LLVM because it uses something called static single assignment. So it means that you have when you have a conditional, you have to choose if you're going to do this thing or that thing. So you're going to need new basic blocks, and you're going to sort of, depending on your condition, going to go to the one or the other. And then when the basic blocks meet again, you have to do something weird to make the things from the two basic blocks end up in the right place. So the interesting bits is this. This is the conditional branch instruction that generates jumps to one or the other. Here is the branch that ends the then part. Here's the branch that ends the else part. And here is the thing where you join things back up again, and you have to have a phi instruction, which doesn't turn into any real instructions. If you've ever done SSA, you know what a phi instruction is. If you haven't, you can ignore this. Well, until you try to do this yourself. Booleans, comparing, you use floating compare with floating point ordered less than as the opcode, and then that's the only thing here. Date, there isn't much to dates. There are no arithmetic on dates or anything. You can just have conditionals and date constants. And dates were just word 32, so I just passed those around. Yes, what about assets? So we have this type. It's a list of dates and doubles. So I'm going to, so at runtime, we need to take a date and we need to find the corresponding value for it. So this is what we must generate machine code that looks up the value in that list. But I do have the list. The list is right here. So I know how many elements there are. So I could generate a loop that looks through some data structure. But I'm instead going to generate straight line code. This is a really bad idea if this list has thousands of elements. But for my example, where it has 2 elements, that works quite well. So I'm going to change my gen asset function a little bit. All the others, they took an expr and returned a gen asset here. So I'm going to change it a little bit. It's going to take an expr, which will be the asset thing, the date that you want to look up, and it's going to return the lookup value. So it's an asset, okay, and we have the date that we're going to look up. Here is the function that will generate the straight line code that will do the lookup. So if we get to the end of the list and haven't found it, then I'm going to say, okay, it's going to be 0. That's what I did in the interpreter as well. If we have some date, well, we have to see if it's equal to that date. So we need a conditional. We do a compare. I think there's a missing bracket here. We do a compare equal to the date. If that's the thing, no, this is all right. Has to compare equals, take the opcode how to compare. There's one thing, the D, the value, and here is the constant that we're comparing against. So if the comparison comes out equal, we're going to return this value. Otherwise, we recurse and generate code for the rest of the list. So this will generate a bunch of compares, return the right value, another compare, and so on.
So Lennart,
yeah.
The type for gen asset here, you can say it takes an expr 2.
And returns this thing, yes, yes.
So that's another, an asset is basically a data double function.
It is.
So that's another staging, some staging variation on data double function.
Yeah. And indeed, in my previous version of this talk that I gave at Skills Matter, I actually represented assets as functions from date to double. But that has other complications. Yeah, so we modify the observe function a little bit for in gen double. So we generate code to produce the date, and then we pass that date into the gen asset function that will then generate the actual double. So we're almost there. Now we can generate code for an expr that is sort of type double or bool or whatever. But what we really have is this function. This is the thing we want to generate code for. We have a list of assets and a date, and then we have this E double. We don't really know how to generate code for functions yet. So this first argument is static. So that's going to be handled it will be unfolded. So it's only these that are interesting. So this is the thing that we need to generate code for. So we need a function that takes one of these, and it will generate the machine code function that we want. So if you do embedded languages and you deal with functions, you need to have something that have functions around. There is a standard trick. You need to augment your expr type with some kind of variables. And then when you generate code or whatever you do, you need to have an environment around where you can look up variables. So I'm not going to go into the details. You can look at these slides later on if you want to see. So everything will change a little bit. We'll need an environment here. And when we get to variables, we'll look them up in the environment. And then This is the actual function that takes an EDate into an EDouble. We do it by inventing a couple of variable names and doing an environment, generating function for the double, or the code for the double, and then returning that. So this will be the function that takes two EDates, generate codes for the final return value, and returns it. And this is just the top level thing that will test it. So I have to have a little benchmark if I'm claiming that I've done this for efficiency. So it calls this best of function 10 million times, has a list of 3 assets. Okay, let's do these. So if we do the shallow embedding, it took 3.7 seconds to run. So the deep embedding with the interpreter, so the thing I showed you first, that took about 15 seconds. So it's about 5 times slower to do an interpreter on the shallow embedding than it is to do, an interpreter on the deep embedding than it is to run the shallow embedding directly. And then the LLVM version, that is when we generated machine code to evaluate this, takes about 0.3 seconds, so it's about 10 times faster than sort of the original Haskell one. Yeah, isn't much to say. So on this one, I actually have the top level loop, the thing that iterates 10 million times. That bit is actually written in C to avoid the overhead of sort of 10 million, looping 10 million times in Haskell. I didn't trust Haskell to generate good enough code to loop 10 million times. I guess I could have figured out how long that took. But. So I think these are typical numbers. Order of magnitude from interpreter to Haskell running it, and then here we generate machine code. So I must say that it's a bit unfair, because here I'm sort of generating straight line code for the lookup in my asset, whereas Haskell has to deal with the list, that it has to go down the list. So Haskell sort of in some sense does more work than this one does. But that's exactly the trade-offs you can make when you're compiling your embedded language. You get to decide if it happens at sort of compile time or run time. So yes, this version does less work, but it does less work because it can get away with doing less work. Well, the conclusions are, I think Haskell is very good for doing typed EDSLs, shallow embedding easy, deep embedding difficult, but more efficient if you generate machine code. All right.
Thank you very much, Lennart. Any questions, folks?
Now that we have LLVM, is there any point in generating C code anymore? I mean, why would you still do that instead of generating LLVM?
Well, so for instance, in the example John showed, he generated C code because they're targeting some weird signal processor that probably LLVM doesn't have a code generator for, but there is a C compiler for it. So
it's also easier to produce C code than LLVM code.
Yeah, not. So it's producing LLVM code is not that difficult. You can produce quite crappy LLVM code, and the LLVM optimizer will do a good job on it.
So if I decided that I didn't want an EDSL after some time and wanted to make a non-embedded, standalone domain-specific language, I have to write my own parser and so on for some source syntax as I embed. Can I piggyback on all the code generation stuff?
Yeah, I mean, if you're happy with writing your compiler in Haskell, I mean, this took an expert and generated the machine code. So if you go for you're making your own compiler for your DSL, you do your parser, you do your type checking, you produce an expert, then you just reuse the rest of the stuff.
And the non-embedded one is just the front end to the embedded.
Yeah.
How does the effort compare? It seems that the shallow embedding is quite straightforward. How much effort would be required to improve the time of that implementation with type limiting or more primitive type use or eagerness in Haskell versus writing an entire new compiler?
So you could probably improve that one quite a bit with much less effort than it is to sort of write an LLVM code generator. I mean, it depends a lot on what your language is. So in the particular example I had here, there's not really that much you can do in the shallow embedding because it used regular Haskell plus for plus and so on. So I mean, you can have different choice of data structure for your asset. That's about the only thing you can do for this particular example. But this is not really realistic. I mean, in a real language, there are many more things. So there will be more places where you could improve things. But I wouldn't say that you should go sort of the LLVM route immediately. Do it the easy way first, and if that's not good enough, then tweak that, and then if all else fails. Yeah.
So one question I have is, it seems like you know, you end up building like a certain set of tools when you do this. And because I mean, there's the whole details of LLVM, but there's the details of the Haskell syntax, right? You actually kind of want to use as much of Haskell's syntax as possible. And it seems like if you really build this out, there's a lot of duplication, right? And like, is the thing that you built something that somebody else can take and reuse, which is this very high-level Haskell system for generating LLVM?
So I think you can redo this to be much more usable. So the feldspar stuff that John mentioned that generates C code, that is built on top of a framework which is sort of very extensible when what kind of constructors you have and so on. So if you started from that instead and generate LLVM code from that, I think you could get something that's quite reusable, but I haven't done that.
And you've got a general purpose language rather than the DSL.
Well, I mean, you can certainly make a general purpose language. I mean, but it all depends on what you're doing in your front end there. If it's
just written a compiler.
Yeah, and that's fun.
And on that note, I think we have room for one more question. There's a hand coming up there.
How would the benchmarks be different if you made 3 cores that had 10 million assets instead?
I have no idea. I ran the benchmarks at 7 a.m. this morning, so I can't say I've done extensive research.